Faster AI chips get the headlines, but memory is the silent bottleneck currently choking modern large language models. Think of an AI model as an industrial kitchen tasked with cooking a massive banquet. Here, compute is simply how fast your chefs can chop, sauté, and plate the food. Memory, on the other hand, is the kitchen's counter space. You can hire the fastest chefs on Earth, but if every square inch of stainless steel is buried under dirty bowls and scattered ingredients, the entire line stops. When artificial intelligence systems hit a wall, they rarely crash because they lack the brain power to think faster. They crash because they physically run out of room to place their temporary data. The main culprit hoarding this digital counterspace is a component called the standard attention mechanism. To understand the context of a prompt, attention requires every single word, or token, to mathematically compare itself against every other word in the sequence. This chart plots sequence length against memory. Notice the flaw: quadratic memory complexity. Memory doesn't scale evenly, it multiplies, triggering an exponential vertical spike. In our kitchen, chefs grab a new bowl for every ingredient combination. Within minutes, the shared workspace is totally buried. Without writing entirely new rules for how data is stored and accessed, scaling these models to billions of parameters hits a hard mathematical ceiling. To bypass that ceiling, engineers developed strict new architectural rules. The first is flash attention. Flash attention uses tiling to break massive data inputs into smaller chunks that fit strictly inside the GPU's fast shared memory. Inside, it performs recomputation. It discards completed attention matrices, keeping only tiny normalization factors to recalculate data on the fly. This is the exact equivalent of a chef meticulously washing and wiping down their cutting board immediately after every single task. By treating a slight increase in calculation effort for an infinitely reusable workspace, flash attention effectively neutralizes the sequence length bottleneck. But reading a prompt is only half the job. When the model shifts to generating text, a phase called inference, it creates words one at a time. Rereading the entire sequence to generate a single new word is a massive waste of resources. This requires a second architectural efficiency: KV caching. KV, or key value caching, securely stores the mathematical states of previously generated tokens. Instead of recalculating the whole sentence, the model only has to actively compute attention for the single newest word, referencing the cache for the rest. In culinary terms, this is mise en place. You chop your ingredients before service and store them in neat containers on the line. When an order comes in, you grab exactly what you need, without ever having to prep a whole onion for a single dish. By keeping past data in a readily accessible pre-processed state, KV caching eliminates catastrophic amounts of repetitive memory load during real-time generation. Let's zoom out to the ultimate scale challenge. Training a modern foundation model requires thousands of GPUs working together because the model is simply too massive to fit on one. Traditionally, systems use data parallelism, where every single GPU is forced to hold a complete identical copy of the model's optimizer states and parameters. It works, but it wastes an immense amount of space. To solve this, engineers use Zero, the Zero Redundancy Optimizer. Zero slices these massive states into smaller partitions and distributes them across the network of GPUs, eliminating the duplication entirely. Instead of 100 chefs cluttering personal stations with identical massive recipe books, they partition the knowledge and share a single master copy. Zero transforms training from a redundant memory trap into a highly scalable linear system. To grow the model, you just add more shared hardware. The combination of flash attention, efficient KV caching, and zero parallelism allows developers to bypass the storage constraints that once halted model growth. These specific techniques achieve a critical milestone. They decouple the growth of an AI model's memory footprint from the length of the data it processes. Without these spatial optimizations, models like ChatGPT or Claude simply could not run on modern hardware. They would hit a memory wall long before completing a single response. Scaling AI has shifted from a race for sheer speed to a contest of architectural elegance. Success is defined by utilizing limited workspace. Future growth in large language models relies on this meticulous efficiency and the ultimate mastery of the counterspace.